Okay, good morning, everyone. 1 week from right now, exam 1. Dun dun dun. I know it's terrible. You're going to be okay. You're going to survive. Be doing the homework. This weekend, do homework. I can't overemphasize enough, do homework. You saw that some of the assignments have been changed, so you've got 3 homework assignments you need to be worrying about before the exam, even though they're due a few days after the exam. The other 2, after looking through the assignments, I saw that most of the problems, they deal with difficulty levels that we're going to cover after the exam. So it's still Newton's law stuff, but it's just at a higher level than what I wanted to deal with in the first exam. So I'm going to be posting a few additional, say, practice problems dealing with Newton's second law and free body diagrams, not for credit or anything, just to help you prepare as we get closer to this first exam, okay? We're going to finish up material today. There's just a smidge of new material. Most of what we're going to do today is our multiple choice questions that are in a lot of ways like a lot of mini problems that help us understand Newton's laws, et cetera, et cetera, et cetera, even though we've basically covered most of the new stuff. Where we left off was I gave you this little problem here at the end saying you could use the acceleration that we found in this problem to go back and do one-dimensional kinematics. Let me go ahead and just write that out for you. You can find the time by using this equation. And solving that for time, you should have got 0.88 seconds. Did anybody do this? Just lie. You all did it, right? Yes, you all did it. Fantastic. And you could also find the final velocity by using this equation. And that acceleration is the acceleration we found right there. Okay, so the acceleration is something that's known. So you could find the final velocity to be 5.2 meters per second. Okay, so this one problem connects forces, which is why the objects are moving, back to the actual motion itself, and allows you to find things that are related to the motion besides just the acceleration. Okay, so let's slide forward a little bit and work on a few of these problems. And I'm going to sort of talk through most of these right from the beginning today, just to make sure that we can cover everything that I'd like to. There might be a couple that I wait for you, let you think about it a little bit. But in this particular case, we've got a block that's on an elevator, and the elevator is moving up at a constant speed. We are asked to find the relationship between the force due to gravity, so the gravitational force, and the normal force on the block. So you can sort of just ignore the elevator and everything and just think about the block and what it's experiencing. So let's just draw the block. There's our mass. I'm going to allow up to be the positive y direction. Nothing is happening horizontally here, so I don't really care about that. What is one of the forces that's acting on the block? Go. Gravity. Which way is gravity? Down. So let's go ahead and draw that in. Oh, let's go with this color. We'll just make things interesting today. Ooh, gravity. What's another force that's acting on the block? The normal force. It's resting on the floor of the elevator, and that's supporting it, right? And keep in mind, normal forces are perpendicular to a surface, so we have a normal force in this direction. Is there anything else happening to the block? Don't think about what's going on with the elevator or anything, just be the block. Does it feel any other pushes or pulls on it? No, that's all. It's like I'm being supported from below, and I also feel gravity pulling me down. That's it. So let's write out Newton's second law in the y direction and just see if it leads us to the answer, the relationship between gravity and the normal force. Well, if I'm moving at a constant velocity, that means the acceleration is 0. The velocity is not changing. So I can say that I have a normal force that's in the positive direction and a gravitational force that's in the negative direction. Those are equal to 0. And let's go ahead and plug in for the gravitational force and put it on the other side. We get the normal force in this case is equal to the weight, to the gravitational force. And you can see that is answer number 2 with with slightly different variables. Okay? Now keep in mind, we've all ridden an elevator. Yes? That'd be kind of strange at this point if there's some of you just like, nope, I see elevators, I just skip it. Maybe some of you have, I don't know. But elevators, right? There's a period of time if you're going to a higher floor, right, where it goes from rest, it speeds up because it has to start moving, but very quickly just reaches a constant velocity and just goes at that constant velocity until it approaches your floor when it slows down and comes to stop. So there's two periods of acceleration, a speeding up, a slowing down, and in the middle, constant velocity. We're talking about that point in the middle when it's just traveling upward constantly. At that point, you're just standing there. You really should feel relatively normal other than maybe getting jostled around a little bit because the elevator's bumpy, okay? If we were to put you on a bathroom scale, like say underneath the block there, or if we were to put you on a bathroom scale, the bathroom scale actually reads what we call the normal force, which remember had another name, the apparent weight. It's reading how much force it has to exert to support you, okay? So in this particular case, the normal force is equal to your weight. A bathroom scale would read accurately. It would be measuring your weight and your weight alone at this particular situation, okay? If we were to change this, and I don't remember if we do have the other case here, where the elevator is accelerating upward. So this is the period of time where the elevator goes from not moving to moving. And if you're traveling up in this way, we've all experienced it, right? There's that brief moment where you feel a little bit pressed into the floor, right? You feel ever so slightly heavier there just for an instant. If you were standing on a bathroom scale at that point, you would see the needle go up a little bit from what you expect your normal weight to be until it reaches constant velocity and it would go back to normal, all right? We can see that reflected by looking at our equations. Again, on this object, the mass, there is still just normal force and gravitational force, nothing else. That's the y direction. Nothing else is happening to the block. The thing that's changed is its motion. Remember, on the right-hand side of the equation is where we put in something about its motion. So if I were to write out Newton's second law in the y direction, now this acceleration is happening. The block is accelerating in the positive y direction. So we're not going to set that equal to 0 this time, which means I'll still have normal force minus gravitational force, but now it's equal to MAY. Now if I solve for the normal force, we've got normal force equals Fg plus MAY, which is the same thing as Mg plus MAY. Mg is your weight. Notice something is being added to it. The normal force, the support force, is now more than your weight. The bathroom scale reading the normal force is going to be a little higher. You feel a little bit heavier, okay? Do you see the way this interaction between forces happening and the motion are on two different sides of the equation, okay? The forces didn't change, but the motion did, okay? If you just think about what the normal force is having to do here, it's doing more than just supporting you, right? It's speeding you up. So it sort of makes sense that it needs to not just support you, but apply some more force to try to get you to go faster in the upwards direction. Question?
Can you kind of explain what MAY is again?
MAY. So MAY is just your mass times the acceleration vertically, okay? That side is all about mass and motion. Mass and motion. Let's flip it around. Let's, well, first of all, which one of these it's normal is greater than mg? What if we were to go the other way? Okay? What if we were to say, let's say accelerating downward? Which means I would flip the acceleration this direction. Okay? Accelerating downward, but traveling upward. What? Accelerating downward, but traveling upward. Traveling upward still means like, I'm going to a higher floor, going to a higher floor. My velocity is this way, but an acceleration that points the other way is what slows me down. Okay, remember an acceleration isn't which direction you're traveling. Acceleration is the influence on the direction you're traveling. Okay, so I'm still going up. Acceleration is down. That means I'm approaching my floor and my velocity is now decreasing. Okay, what do you feel in the elevator when that's occurring as you get closer to the floor that you're traveling to? You feel lighter there for just a brief moment, right? I'm going up, and then all of a sudden, it's like, oh, I'm coming to rest. There's just that little moment where you feel a little bit lighter. If you were to jump at that moment, you might end up higher in the air than you expected and bang up against the ceiling or something. Don't go do that. Or go find a high elevator and have some fun. No, don't. I didn't say that. Don't go do that. It's a good time, though. No, don't do it. Never mind. So let's see. In this particular case, again, the forces are exactly the same. The thing that's changed is the motion. The acceleration is now negative instead of positive. So let's see what happens. I've got normal force minus gravitational force equals m times negative ay. Or the normal force is equal to Fg, your weight, minus may. So now it's your weight minus a little bit. The normal force or the scale or the support force is less than your weight. And that's why you feel a little bit lighter. Okay? The direction of the acceleration is changing, and how it relates to which direction you're traveling, that's going to change the normal force. In all of these cases, though, the free body diagram looks exactly the same. Who's got questions? Is this a bad way to ask for questions? To lean out here awkwardly and make you feel a little intimidated? I don't know. That can't be intimidating. Yes?
What about the other choices? What would you look
The other choices. So let's see. The second one goes back to the constant velocity. The third one is this case, n is less than mg. Normal force equal to 0 if the elevator's in free fall, which let's hope it's not. In that particular case, you and the elevator are just falling together. It wouldn't be supporting you at all. And number 5 just has nothing to do with anything. Okay, good question. Let's see what's next. Let's keep doing this. By the way, look at this. Wow, somebody really put some effort in on the drawing today, didn't they? Oh, yeah, that is some nice cartoon work. Regular Pixar happening here. Yeah. Or a copy and paste from a textbook from like the 50s or something. I mean, look at this guy. That's terrifying. What is happening there? Not to mention, I think his head's a little too small. Something like everything's out of proportion. He's got these beady blue eyes. I'm scared. If I'm this child, that'd be my face too. I don't, nothing. Ugh, I'm terrified. So anyway, apparently that's a physics student that's pulling or pushing a sled, in which case is the normal force on the sled greater. You can think about this and try to use a little intuition, then we'll do it mathematically so you can see how the equations work out. In which case is the normal force on the sled greater? Who says 1? Who says 2? 3? Same. 4? 5? Okay, 4 of you voted. Good job. Most of those 4, I think, said case 1. Think about what's happening here. Remember, I don't know, let's look for something here. The table right now is being supported by the floor. Okay? What happens if I get on the table? I'm not going to. What happens to that support force? It's more, right? It has to support more. If I'm pushing down and to the right, I'm pushing down at least partially. The ground is now having to support more. That's kind of the equivalent. Like if this person just decides to hop on the sled too, there's more downward force. The normal force is going to be greater. Okay? In this case, you're actually lifting at least partially. which means the ground isn't having to support quite as much. So the normal force is greater in case 1, but let's work that out from a free body diagram perspective, okay? If I am the sled, we've got a normal force, we've got a gravitational force, and now we've got this force that's kind of going up that way a little bit, okay? That force can be broken into components, so let's just call that Fx and Fy. And let's say that up is the positive y direction. We can write out our forces in the y direction, and if the sled is staying on the ground, then it's not accelerating up or down, so that's 0. And then I've got Fn plus Fy minus Fg equals 0. I've got 2 forces that are pointing up, 1 force that's pointing down. Well, let's see what we get. In this particular case, wait a minute, I wanted to do the down one, didn't I? My apologies. Let's go back. Stop right there, and let's switch this around. So sorry. I don't know why I got caught up in that one. So let's change these forces a little bit. We've got this force that is down that direction. There we go. And we'll break that into components, Fx and Fy. Okay? So this is case 1. We've got this force that's down and to the right, so it's some to the right and some down. So you can see that now I've got this one up and these 2 forces that are down. All right? So if we write those out, I've got minus Fg minus Fy equals 0. And then Fn equals Fg plus Fy. It's not just supporting the weight, it's supporting some of that downward force as well. So it's more than the weight. If I do a free body diagram for the last one, it switches the sign, which means it would be the weight minus some force. So case 1 is more than the weight. That's a larger normal force than normal. If you're not pushing or pulling at all, well then that just goes away and the normal force is just supporting the weight. Okay? See how these equations sort of interplay a little bit? Are you feeling okay about free body diagrams? Are you feeling terrible about free body diagrams? Yes.
Why are you taking out the Fx? Are you only doing it in the y direction?
I'm only doing it in the y direction just because the problem asked me about the normal force. And the x direction won't have that in there at all. So we could, but there's no need to. All right, let's go over to this one. Consider 2 identical blocks. They're talking about the red blocks. One is on a flat surface, one is on the inclined surface. Which one has more normal force? A, B, A, B, A, B. Okay, I see some A's out there. You're right. A has more normal force, but why? Both of them have a normal force and a gravitational force. Okay, that looks something like that. Keep in mind, here, the normal force is exactly and totally balancing the gravitational force completely. Okay? In this particular case, notice they don't point in opposite directions. The normal force is balancing a component of the gravitational force, but not the whole thing. All right? So here, this is going to be less of a normal force. And you can imagine if I tilt this more and more and more, eventually I tilt it so much that the normal force isn't there at all because it's no longer underneath the block, right? So you can imagine the normal force is greatest when it's flat, and it becomes less and less as I tilt it more and more toward vertical, right? And it's a function of that angle. Okay? Everybody's doing all right? I can't tell if you're doing all right or not, so we're just going to continue because I want to talk about friction, right? So, Newton's second law, we dealt with some problems with that. We're going to add one more special force before we sort of finish up stuff for this first exam. Don't think of this as like, brand new problems and information. I'm just adding one more force that we're going to take into account on free body diagrams just like we did, okay? So let me describe how friction works, and then we'll do a problem, even though I left the problem out of the slide, so we'll insert a slide and I'll tell you about the problem in a second. So friction, I think we all kind of understand what friction is. Like we have a basic feel for it. You've probably been thinking about friction and wanting to use friction in problems, even though all the problems so far are saying like, there's no friction, it's icy or frictionless or something like that's happening. Let me just say that friction is, we will say that it's a force between surfaces that opposes motion. Or specifically, we'll say sliding motion. A force between surfaces that opposes a sliding motion between those surfaces. So let me draw a couple of surfaces. Let's say there's some object in the bottom of it, like this. And then it's in interaction with some other surface, and maybe it looks like this. And you're thinking, what ridiculous surfaces look like that? All of them. No matter how smooth they feel, if you zoom in far enough, like even like this door here, right? I touch this and I'm like, smooth door. I don't know why I'm petting the door now. Things just turned weird, all right? But smooth. If I zoom way, way in, I'm not going to see smooth. I'm going to see sort of peaks and valleys and pits and things. Like it's going to be an irregular surface. In fact, just the fact that I can touch this and sort of feel it at all, like it's like, oh, I'm feeling that roughness even though my finger can slide over it relatively smoothly. If you zoom in far enough, it looks like that, all right? So you can imagine like there is just a certain amount of roughness here, and if I try to move those two surfaces relative to each other, well, clearly they're going to kind of, make that sort of difficult, right? Some of the peaks and valleys are going to interact, and it's just going to be hard for them to rub against each other. Also, well, before we leave that, let's say there is a measure of roughness, and we could say that more roughness should lead to more friction. So that makes sense. But also, if I take these two surfaces and either barely touch them together or push them together more, right? If they're barely touching, well then all those little grooves aren't going to impact each other very much. But if I push them together really hard, well, it's like I'm pushing the peaks and the valleys sort of together and then try to slide them, it's going to be more difficult. There's going to be more friction there. So if there's, we'll say, more pressure, not exactly pressure. It turns out if you think about it, like if I push down on the top surface, the bottom surface has to support that. What we're really talking about is more normal force. Then we're going to have more friction when I try to slide those transverse to that force. So these are the two things that will be in the equation. And I'm going to start down here with kinetic friction. It turns out that the force of kinetic friction is equal to a new symbol, Greek letter mu. Mu. I like mu. Just kind of sounds like fun. It sounds like a sound an animal would make. Mu. Mu. I don't know what kind of animal it is. Mu. Mu. You get the idea. Mu sub k for kinetic times the normal force. This mu sub k is a measurement of the roughness, and it is known as the coefficient of kinetic friction. And for a given pair of surfaces that are interacting, it will just be a set value, a constant that someone measured experimentally. There's a table of them in the book. I could also have you solve for it, assuming I give you everything else in the problem. If that number is bigger, there's more roughness, you're going to get more friction. If I increase the interaction between the two by pushing the two surfaces together more, there's more friction. If it's frictionless, what we're saying is that basically this coefficient is 0, so that there's no friction force, okay? So coefficient of kinetic friction, keep in mind, this word kinetic is all about motion. We're talking about a force that occurs, that's not how you spell, occurs when there is relative motion between the surfaces. So something is sliding against something else, okay? So in other words, if I take my hand and just drag it across the board, well, clearly there is motion between the surface of my hand and the surface of the board, and I can feel that opposition. There is kinetic friction that's occurring between those two surfaces at that point. This differs from the more confusing one, static friction. So the word static is like, oh, it's just staying the same. It's not moving. How can I have friction if nothing's moving? I'll explain in a second. This one occurs when there is possible motion between surfaces. It occurs when there is possible motion between surfaces. So, let me move this over here. I'm going to move this right here. And I'm going to use this thing as an example. Okay, so are you ready here? Here it comes. Possible motion. Right now, this thing's just sitting here on a flat table. It's not really possible motion right now for it to slide sideways. It has no reason to. There's no sideways force to give it a reason to change its current velocity. So it's just going to keep its velocity equal to 0. So right now, there's no friction force between the bottom of it and the table. But if all of a sudden I decide to push on it, I'm pushing just a little bit. It's not moving. As soon as I started pushing on it, though, friction occurred because now I'm giving it an option to move. I'm trying to move it. I'm not trying very hard. So as soon as I pushed a little bit, friction said no. And it opposed me, okay? It didn't have to oppose me much because I didn't push very hard. But you can imagine if there was absolutely 0 friction, just pushing a little bit, it would have started to move. If there was none, 0 friction, which is a little bit hard to imagine, okay? So I say like, well, I need to push a little harder apparently. I'm pushing a little harder. Friction is fighting a little harder. So the friction force changed. It's not a constant value. So I push a little harder. Push a little harder. Push a little harder. A little harder. Oh, finally, it starts to move. I reached a point where whatever friction is possible between these two surfaces maxed out, and it couldn't oppose me anymore. I defeated the friction. Okay? So you might think of this as an inequality. The friction force starts at 0. And we'll write this as F friction static, and it goes up to some maximum value. Okay, it ranges from 0 up to a maximum, and that maximum is equal to mu static times the normal force. So this is the maximum static friction. If I push harder than that, well then friction has maxed out, and I've defeated the static friction. Once it starts sliding, we're not dealing with static friction anymore. Things are actually moving. Now we have kinetic friction. So it depends on whether there's possible motion or actual sliding motion between those two surfaces. Okay? You see the difference between the two? The only real difference is one is variable, but once you get to a maximum, it's the exact same equation. And kinetic is a constant value. So, let me explain the difference between these two in a situation that maybe you've had before. You ever helped a friend move? I'm sorry. It was terrible, right? Your friend called up, like, hey, I'm moving this weekend. Give me a hand? And you're like, no, I really don't want to. And I just have It's a few boxes, a couple of big items, but not a lot. And you're like, fine. It'll just take an hour. Fine. Then you get there, and you're like, we're friends and everything, but I really hate that I'm here this morning because, like, look around. You haven't packed anything. And those two items you said that were kind of large, understatement. One is a piano, right? And it has no wheels or anything, and the other one is like a car with no wheels. And you're like, thanks for this. This is great. Why did you do this to me? We're not friends anymore. Officially, it's over. So you say, like, fine, let's start with the piano. So the piano's there, and you're like, we have to get it to the door, so let's start pushing. So you and your friend say, all right, here we go. And it doesn't move. Static friction. You tried to move it. Friction said, I don't think so. And we're going to stop you. So even though the surfaces might have been somewhat smooth, there was so much normal force because of the weight of the piano and the ground supporting it. It was pushing those surfaces together. So you say, we're going to need more friends, or, well, after today, former friends. So you call up some more people, now there's 4 of you, and you're all like, ah! And it doesn't move. Okay, you've increased the force, and the friction just laughed and increased the force back. So then you get all of your friends who are never going to talk to each other again, and all of you decide to start pushing, and then it's like, push harder, 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 yeah! And then it starts moving, and you're all like, hey, this is fantastic. This isn't too bad anymore. Something changed in between those two states. Once you get the object moving, you really kind of don't want to stop because, and it's not just a matter of like, oh, like we've got some momentum going or something or other. No, you actually changed the type of friction. You went from static friction, which you had to overcome, to kinetic friction, and it turns out that these coefficients are different. Kinetic friction coefficient, in general, is less than the static coefficient of friction. We'll say for a given surface.
Is it because static friction has more normal force? Is that what it is?
No, the normal force is exactly the same. It's just that if you take experimental measurements of how much opposition is put up by a surface when something is moving over it, versus when something isn't moving, you get a different value. Okay, the normal force is exactly the same. The coefficients are different, which results in different values for F. Here's the way I like to think about it. Would you like a non-scientific explanation that's ridiculous?
Yes.
Yes, wow, that was fast. What if it's more ridiculous than you ever bargained for? You're good with that? You're not going to regret this. I don't even know who's talking back there. I don't see anybody talking. I think someone's like lying on the floor. Like, no. They're just like randomly answering. So, ridiculousness is coming. Okay? So imagine, if you will, that you zoomed in on this floor. Remember, I drew these little sort of nooks and crannies that are there. Zoom in farther. Here's what you're going to see. You're going to see these little creatures. They're called frictionites. Again, non-scientific explanation. Okay? Frictionites. They're all buried into the material up to their armpits. Okay? So it's just like all they have is like a head and arms, like just flailing around down there. Okay? Well, anytime you decide to try to push something sideways, all of them just throw their hands straight up in the air and say, don't move it! And they're like pushing with their little fingers and arms, trying to keep you from sliding the object sideways. Okay? You push a little harder, and they say, no, don't move the object, right? So, you and all your friends pushing the piano, you're all up here going like, ah! And the frictionites, if you would just stop and listen for a second, you would hear, because they're trying to oppose you, okay? The thing is that a very awful thing happens when you finally get the object moving. You don't realize the damage you have done. Because what happens is all those little arms, and again, they're just kind of stuck here, right? Stop the object. At some point, you're pushing harder and harder and harder and harder, and they're like, oh, push harder, stop the object. And then finally, they reach a point where it cannot push any harder. You've hit this point. So they all are like, maximum static coefficient reached. We can't oppose this anymore. And then you push a little harder, and all the arms go and break backwards. I know, it's the worst thing ever. All the little elbows are torn apart. and just like bones are hanging out the skin, and they're all like, ah, as the object slides across the top of them. I told you it was ridiculous. Completely, absolutely ridiculous. So again, if you stop your own screaming and grunting and just listen, you hear them go from ah to ah. There's this sound that's just awful. And now if you imagine like all these little arms, instead of being like this and you're trying to push against it, they're all just kind of laid back as a nice little platform that your object can slide over the top of. And they're not happy about it, but you're kind of happy now. Okay, are you still okay with the ridiculousness? So I can take it to another level.
Yeah.
I don't know if I have another level. But if I think of another level, I'll definitely go there and we'll just test how much you can handle of just absolute stupidity. So, frictionites. Are you not writing this down? Like, frictionites are little creatures that live in surfaces that require extreme magnification to see, and they fight movement against the top of them. Do I need to repeat? Because nobody's writing. Fine. Fail the test. If I ask a multiple choice question on the exam, and I say, what is the origin of friction? You're going to say, like roughness or something. And I'm going to be like, wrong! Frictionites. End of the story. We're frictionites. So deal with it. So, 3 things here at the bottom that we can notice from the above equations. Okay? First of all, friction is independent of speed. In this kinetic friction equation, there's no velocity. Doesn't matter. Are you moving it slow? Are you moving it fast? There's the exact same kinetic friction fighting that motion. Okay? Has nothing to do with velocity. Second, it has nothing to do with area. Nothing at all to do with area. Do you see an A in that equation? There is no A in that equation, meaning that maybe we have like here's a nice rectangular box sort of thing. I wonder what's inside there. Weirdly enough, until this moment, I have not noticed these doors. Have you noticed them? Well, you've been sitting here like staring at them. As far as we know, there's people in there. I really wish I planned this in advance and I had it like stuffed full of people. That'd be kind of fantastic. What's in here now? We have to find out. Ah! Well, that's just random. Random bunches of nothing. I don't know why I'm looking at this cabinet now. But we all know that next class, I'll come very early and I'll be in here before and then I'll pop out at the last second. No, that's not going to happen either. So imagine this is separated from the wall and we have like this box and it's covered in this paint on all sides. Okay? If I decide to push it on the bottom square like this, there's kinetic friction. If I decide to flip it over on its side so that all of this space is touching, there's a different contact area. Well, it's still the same surface and it weighs the same, so there's still going to be the same normal force. It means the friction is still going to be the same. The amount of friction that's going to fight you is the same whether the contact area is smaller or larger because it's the same item, okay? Normal and mu are the same thing in that case, all right? So don't think like, hey, this would be easier if we slide the piano like on its side. I don't tip the piano on its side. It's not gonna help anybody out, all right? The only thing you can do to help, perhaps, is find maybe if one of the sides is smoother, you know, it has less frictionites, then you might be in better shape. But if all the sides are the same, it's not going to help. And then finally, this will help us with our free body diagram. The friction will be parallel to the surface, and it will be opposite to any motion or the potential motion, okay? Opposite to motion or potential motion. So let's go over here and let me put a new slide in and let's actually work a problem. Let's put it there. Good enough. I'll try to make the thing bigger, but I can't really tell which parts are on the screen and which are not. So let's say we have a problem that looks something like this. We have a flat surface. We are going to say that it is covered in frictionites. Yeah, that's how you spell it, frictionites. There is a box that's sitting on the surface, and there is a string attached to the box, and someone is pulling on the string in this direction because Their hand is up here. That is a beautiful hand. You gotta love that. And they're pulling kind of up that direction. Okay? You can imagine there's a person attached to that block hand or whatever it is. So we have a frictiony surface and a hand with a string pulling on the box. And we're going to say a couple of things. This results in horizontal acceleration, but no vertical motion. So in other words, applying the forces, you're able to drag the box along the ground, but you're not pulling up enough that you actually lift the box, which you might imagine would happen if it was really, 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 really light. Okay? So let me give you some numbers. I'll give you some numbers. Why not? Let's say that the mass is 34 kilograms. This angle is 17 degrees. The coefficient of kinetic friction, so we're going to look at it after it's already moving, is 0.1. And then finally, I'll say the tension force is 1,000 newtons. I kind of hate having to look at this flyer all the time because the biggest word here is trash, right? So I'm on the other side of the room, and all I see, like walking around, it's like I'm trying to do a good job, I'm trying to teach you things, and I look over there, it's trash. I feel like it's talking to me. It's not very nice. I don't like that. And underneath that is a hand saying stop. So it's like, you're trash. Stop lecturing and leave. I need to take that down. We need to put that elsewhere. We could put it outside, but then people on the outside would be like, whatever's happening inside there is trash. And that's insulting as well. So I don't know what to do about it. We'll figure it out. So I've given you some numbers. Let's work the exact same steps I taught you on Tuesday. The 5 steps to work a free body diagram problem. And we'll just see what the unknowns are, and we'll solve for them at the end. Okay? So there's a diagram of the object. That's step 1. Beautiful. I just drew a smaller box. We're going to say that the object is moving to the right where it has acceleration. So I'm going to let that be one of my positive directions. We'll say that's plus x. And perpendicular to that, we'll say we have our y direction. And now you are going to tell me a force that is acting on our box. That's right. It's a very good answer. What's one of them? Gravity? Gravity? Which way does gravity go?
Down.
Down? What else? Yeah, the floor or the ground or whatever is supporting the object, so it goes right up. What else? Which way would the friction be? Left, right? So parallel to the ground and opposite from the way it's moving. Okay, so the frictionites are all sort of pushing that way. So that's force, friction, kinetic. What else? What was that? I think I heard the right answer. Yeah, tension. Tension pulls. There's a rope attached to this box that's pulling sort of up that direction. We've got 4 forces that we're dealing with. That is all. Those 4 forces define the motion of the object. It's the result of those 4 forces that makes the box accelerate to the right. Okay? So let's really quickly go ahead and break up the tension force into 2 components. There is a component of it that's in the x direction, a component that's in the y direction, and that angle inside there is theta. So this bottom side would be what? Cosine. It's the adjacent side, so I know I'm going to use the cosine, so it's going to be ft cosine theta. And the other side is the opposite of that, ft sine theta. Notice they're both positive, to the right and up. Okay? So now when we've done that, we can write out an equation for the sum of the forces in the x direction and an equation for the sum of the forces in the y direction. And we are going to just obey the equations and see what they give us. Trash. I see you, poster. Ugh. By the way, this morning started very sleepy. So sleepy. So incredibly sleepy when that alarm went off at 5:30. I was like, I cried for a little while. I just laid there and sobbed. And then I went to the shower. Sobbed some more. And then I started making coffee while sobbing into the coffee cup. And then I had coffee. And then life started to get a little better, but still sleepy. So I had more coffee. So I've had a little bit more coffee today than normal. I don't know if that's been reflected in anything at all, but things have seemed a little weird here today. I think I need to increase the intake a little more. We could have all kinds of fun. But I also know that before long, I'm going to crash. I'm going to crash hard, and I'll be back to the sobbing and the sleepy. So you may find me somewhere on campus this afternoon, just in the grass. Sleepy. So, we'll see what happens. That 3:30 class I have this afternoon should be fun. Huh. More coffee. More coffee is coming. Never mind. In the x direction, we've got positive ft cosine theta pointing to the right, and we've got negative friction pointing to the left. So minus f friction kinetic. Those things result in acceleration in the x direction. The definition of the problem said it's going to accelerate horizontally. Only those two forces, one left and one right, are occurring in the x direction. Okay? Yes? 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 Yes. What about vertically? Notice I've got this one pointing up, this one pointing up, this one pointing down. Those are my three vertical forces. So we'll write two of them as positive, and one of them as negative. What's up with the acceleration vertically? 0, right? The problem said no vertical motion. So this acceleration is 0. So the right-hand side of that equation is 0. Those are the two equations. If I didn't want to do step 5, I didn't care about any unknowns, and maybe the problem was just like draw a free body diagram and write out Newton's second law for both directions, would be done. Okay? But I want to see how far we can take this problem. So let's plug in any other equations that we know. I don't have an equation for tension, so I'm going to just write this down. I do, however, have an equation for kinetic friction. So let's go ahead and plug that in. Looking at this equation, I know the tension, I know the angle, I know the coefficient of friction. I don't know the normal force, and I don't know the acceleration. I've got two unknowns. I can't solve anything there. So I'm stuck in the x direction. Have you ever been stuck in the x direction? Yeah, I know, it's tough. What are you going to do? We are stuck in the x direction. And alas, we are going to move to the y direction somehow, even though we're stuck. Okay? So in the y direction, well, there's not an equation for the normal force. And once again, there's not an equation for tension. But there is an equation for the gravitational force, and it is mg. So I'm going to go ahead and plug that in. Once again, I don't know the normal force, but I do know tension and theta and m and g. Yay, there's only one unknown here, which means I can solve for it. So let's go ahead and solve for the normal force. We'll find out how much the ground is supporting this box. So Fn is equal to minus Ft sine theta plus mg, and we will plug those numbers in and see what we get. And I'm going to need your help because I don't have this problem actually worked. I have a variation of it, but I decided to take out one of the forces because we haven't learned about it yet. So I don't know what the answers are. So let's see, 1,000 times the sine of 17 plus 34 times 9.8. And I'm trusting you are going to give me the correct answer, and so is the rest of the class. If you give me the wrong answer, then someone else in the class is going to be like, you're wrong, and say the right answer. So be careful and double check your work, not to scare you or anything. By the way, I think I need your shirt in the back, the one that goes from exercise to bacon. I don't know how you get from one to the other, but I'd like to get from there. So let's see. Exercise, size, XR size.
Eggs are sides for.
Eggs are sides. I like that. For bacon. Yes. You know, given bacon, I'd exercise for bacon.
I do that almost every morning.
You have bacon and then exercise?
No, like as soon as I wake up, I exercise at a local gym and then I come back.
And then you come back and have bacon.
Yes.
You know you should put bacon on both ends of that. No, not bacon before exercise doesn't result in.
I've been trying to lose weight for a while.
That's the problem. Less bacon in this world. Solve a lot of problems with bacon. I like bacon. Anybody have this number? I'm just stalling. Anybody? Now you don't want to tell me because you're worried you're wrong, right? Anybody have a number? We'll see how it compares to others. Just shout it out.
40.82.
40.82. Somewhat in unison. 40.8-ish. I feel okay with that number. We'll see if anybody decides to disagree before class is out. For now, we'll go with 40.8. Which means that I now have a number that will go up here and save us from the x direction. Okay? The other unknown that was there was the acceleration. So let's solve that first algebraically, which is ft cosine theta minus, whoops, I'm quickly running out of space here, minus mu k fn, and divide the whole thing by m. And I'm going to just let you punch those numbers in and tell me what you get. So I will wait once again and find another way to stall by answering a question. That's good. What's up?
Do you have to put a negative for the 9.8?
The negative has already been done elsewhere. So you're putting in a positive, a magnitude for G, because essentially we took into account the direction of G when we drew this down, and then when we put a negative sign there. So we've already accounted for that negative sign. Don't do it twice, or you run into problems. Good question. Who's got the acceleration? Nobody? Think anyone outside would help us? What'd you get?
About 28.
28?
Yes.
Okay, I'm fine with that. Well, that's a lot of acceleration.
Yeah.
Of course, 1,000 newtons of tension force is a lot of force. So these are the movers you want to hire, apparently, because they can really accelerate a box. It's impressive. Anybody have questions? It's just like what we did on Tuesday. We just put in one new force. Yeah.
What are we solving for? Like, what's the
Well, if you look back at our directions, step 5 was find the unknowns.
That's it. We're just saying.
In this particular case, our two unknowns were this one and this one. Okay. Who else has questions? Okay. So, a couple of different things. I've got a bunch of these multiple choice questions, both earlier in the chapter I'd like to talk about. We'll go back there in a little bit. And some here that deal with friction. And I also want to briefly talk about Newton's third law, but we don't do much with it in this class. All you kind of need to know is like the concept for the test. We'll use it a little bit more in the next chapter after our first exam. So, if I have a box that's in a pickup truck sitting in a frictionless truck bed, boy, that sounds completely invented. What truck is frictionless in the back? When the truck accelerates forward, if this is frictionless, the box just slides right out of the back, which is why this is a, well, invented and useless truck. Unless you have the door at the back all closed, then it would help, I guess. So why does it slide off the back when the truck leaves? No, we don't really deal with air resistance in here. So does friction, did the truck go and friction was like, hee hee, remember frictionites? leave box, and they just threw it off the back. I don't think that that's the way friction works. Instead, if we had friction, the box would have stayed in the truck. It's the fact that there was no friction that the box left. Instead, it's because the forces added to 0 that the truck left, and the box stayed right where it was, right? It's like, I'm here, bye-bye truck, and then it just fell to the ground, okay? The fact is there was no net force to help the box move along with the truck, which would happen if there was friction. So back to this, and again, is this the exact same dude? Yeah, that's him. Creepy. Can we see his eyes in this other diagram? Not so much, but you get the idea. So for whatever reason, this is, well, now it doesn't say physics student. It just says you, so I guess you're a physics student. So we already know that this one has higher normal force. But now it's asking the easiest way to accomplish this whole ride on the sled. Clearly the answer is number 5. There's nothing easier than that. But I don't think that's the point of the problem. Yeah, that's just, no. So that's not quite right. One of these results in less friction, which would make it easier to pull the sled. And by saying pull, I just gave you the answer. Because that is the easier one because it has less normal force, right? The snow and the sled has the same amount of friction no matter which way you do this. But the one with the higher normal force is going to result in more interaction. It's like you're pushing the sled down into the snow. It's going to be harder to move because there's more friction in that case. So pulling from the front is the second easiest to just telling her to get out and walk, all right? Let's see. I'm trying to decide which ones I want to do here. Let's do this one before I jump over to Newton's third law. A box of weight 100 newtons, so they've told us the gravitational force, not the mass, is at rest on a floor with static coefficient of friction 0.5. Rope is attached, pulled horizontally with a certain tension. Which way does the box move? So first of all, there's a discrepancy between what's up there in the problem and what's down here in the diagram, so get rid of that. How'd that happen? I don't know. And we're trying to determine whether essentially this tension is enough to overcome the static friction. Are we pulling hard enough to make the box move? So first of all, like, is it ever going to go to the left? Like, unless the frictionites like kind of get a whole new idea of the way they do things, they don't just oppose, but they're like, you put something on me, and they start throwing things, like the box is not going to go to the left. The friction is only going to come into play as I start to pull. So the question is, what is the maximum amount of friction that can happen here? Well, if I look in the y direction, we can see that the sum of the forces in the y direction tells me that the normal force is just equal to the weight. Okay? So that means I could find the maximum static friction force. That's too many subscripts. Let's figure this out here. So let's say friction force, static, max. There we go. I'll write it like that. Is equal to mu static times the normal force. The normal force is just the weight, so that means I'm going to have 0.5 times 100. So that's 50. But I'm only pulling with 30. I'm not pulling hard enough to even overcome the static friction. So that means it's just going to sit there because I'm not pulling hard enough. Don't get the idea that there's like, oh, 30 newtons that way, 50 newtons that way. It's going to move this way. No, again, frictionites don't work like that. Okay? They're just going to oppose whatever you give them. Which brings me to Newton's third law. Unless somebody wants to stop me with a question. Anybody want to stop me with a question? Questions? Questions? No questions? Okay. Newton's third law. You see there with an asterisk sort of the common way of stating this, which sounds kind of ancient, right? I feel like I almost have to use an accent or something when it need to be like proper and like to every action there's an equal and opposite reaction. Like, well, what does that mean? We haven't talked about anything called an action or a reaction. This is just an ancient way of saying what I wrote above, in terms of things that we know about, even though it's really, really lengthy. So notice, we've got, if I have one object exerting a force on another object, so be that whatever it wants to be, like, I don't know, here, I'm an object, here's a second object, I exerted a force on it, okay? The second object exerts an equal force in the opposite direction back on the first object. So I push on this thing, it pushes back on me. I push on the wall, it pushes back on me. Opposite direction, same force. I push on this thing, and even if it's moving, it's still pushing back on me with the exact same force. The problem with Newton's third law, not that it's a problem with Newton's third law, it's a problem with people's understanding of Newton's third law, is that you get into this mindset where it's like, there's one force and there's another force, it's exactly the same. How does anything do anything? How did I just move that if it's just pushing back on me with the same amount that I pushed on it? And you end up like in this little circular reasoning loop where you're just like, nothing makes sense anymore. I don't see how the world works. And it's a little bit frustrating. Did that happen to anybody in high school when you took physics class? Newton's third law? And you're just like, nah, I'm not going to think about it too much because it's bothering me. Yes?
If they even offered.
What's that?
If they even offered.
If they even offered a physics class, yeah. So if they had offered it, then this would have been an existential crisis and then all would have been lost. And yes, I get it, okay? Here's the thing about Newton's third law. Notice, this first force on a second object, okay? So that force is specifically described as being exerted on that thing that I pushed on. This other force, it says, is on the first object. There's two forces that are being described there, right? One of them is happening to this thing when I push on it. The other force is happening to me. Me and this thing are not the same thing. Boy, that is like the most brilliant thing I've said all day, right? Me and this, we're not the same thing. We are two different objects, okay? I think that's pretty apparent, right? I hope so. Me and this object are two different objects. We are experiencing different forces. Even though these two forces are equal, they're happening to two different objects, which is the key to getting Newton's third law right. We could say that the two forces described are acting on two different objects. Each of those objects gets a free body diagram all to itself. It gets its own very nice free body diagram, which means that one of those forces will be in one free body diagram, and the other force will be in a completely separate free body diagram. Okay? So these two forces occur in different free body diagrams. They are in different FBDs, free body diagrams. So we make a mistake when we decide to say, like, okay, he's pushing on this black box, and the black box is pushing back on him, and then you draw a diagram for the black box and put both of those forces in that free body diagram, just canceling each other out. That does no good. Instead, you would have to draw a free body diagram for the black box. One of my forces would be there. And then a separate free body diagram for me. One of the forces would be in there. And you would just know that, like, hey, there's a force in that diagram and a force in this diagram that happen to be equal to each other. Okay? You will deal with problems like that after the exam. At this point, I just want you to sort of know what the concept is. If I ask you a multiple choice question and I say, I don't know, this is an illustration of which of Newton's laws, you would know it's the third one, okay? Or if I say something about, like, you know, he pushes on this thing and this thing pushes back, what can you say about these two forces? You get the idea. Just understand the concept at this point. The only thing I can add to this right now is just mathematically what this looks like. So we could say if I have the force, we'll say from number 1 on number 2, it's equal to negative the force from number 2 on number 1. The vectors are the same, except one has a negative because they're pointing in opposite directions. That's not too bad, right? I'll show you how it plays out in problems, but not until a week from Tuesday before that'll actually occur. Now, with the remaining part of class, I want to do this next slide, and then we're going to go all the way back to like slide 3, I think, where there's some questions that I do want to step through. It's not new information. It's just a little practice to help us understand these concepts. Let me go ahead and say, though, with regards to the exam a week from today, I'm going to send out an announcement with some details about like what the format will look like, what to expect, how many of these type of questions, how many of that type of question. I can say it'll be a mixture of multiple choice and problems that you have to like show all your work. There'll be some mixture of that. I don't know exactly what the balance there will be yet. I will provide an equation sheet, which I will give you in advance, like today or tomorrow, so you can kind of know what's going to be expected. I will also let you bring your own page of stuff as well with notes and things and whatever. But I will have to put some restrictions on that because if I just say, you can bring a page of notes, someone is going to order a scroll from Amazon and be like, this is one continuous piece of paper. It is a page. And I'll be like, that's just not going to work. So I have to specify size, front and back, and all that kind of stuff.
8.5 by 11.
That's what it's going to be. But I have to spell that out in an email. Otherwise, something happens. It'll be a normal piece of paper. Okay? But I'll tell you, yeah, someone's excited about that. So I'll tell you more about that in an email. Just make sure that you're reading your announcements, etc. Also, Tuesday is going to be totally review. Okay? So if you're like, I got this, I'm going to get 100 on the test, and you decide not to come, I guess that's fine. There's not going to be any new information. But I'm thinking that's kind of none of you. Yes, you need to come hear the review, but I want you to create the review. So be sending me emails with questions. Anything that's not making sense that you want me to take some time during the review, send me an email. I'll work that in because there's just no way for me to go back and cover everything in an hour and 15 minutes. So I have to focus at least a little bit, okay? So let's look at this problem. When you climb up a rope, you do that by pulling down on the rope, right? It's like, but somehow you end up going up. How does that happen? Well, some of these answers are just mean. Agreed? I didn't write this. This is terrible. First of all, you don't go up, you're too heavy. No, get rid of that. That's terrible. Number 5, you pull the ceiling down. Well, no, it just said you managed to climb up a rope. And number 3, you're not pulling down, it just seems that way. Well, that's ridiculous as well. This slows your initial velocity, which is already upwards. I don't even know what that's talking about. Which certainly leaves me with this. Newton's third law says I pull on the rope pulls back on me. So from your standpoint, the rope pulls you up. So why is it so hard? Well, because I have to pull on the rope to begin with the amount of force that I want the rope to pull on me with. Yeah.
One could, if this were a multiple choice question, one could seem valid to look at.
Why is your initial velocity already upward? If you jumped? Yeah. Generally, when I give multiple choice questions, there's a caveat. It's like, choose the best answer. Which, if you're a little confused by one, you're like, maybe that could be, like, there's an answer there that's like, okay, that all out of these options, that one explains the situation best. Yeah.
Do we need to get scantrons or blue books?
No scantrons, no blue books. I'm going to give you the exam, and everything will happen on that exam. So, in the last 6 minutes, let's go all the way back to slide number 3. All the way back to slide number 3, where we get a little taste of Newton's first law once again. If there is a book lying at rest on the table, why will it stay there? Number 3 is the creepy answer. I hope that's not the answer. Why does it not move? It doesn't move because you haven't given it a reason to move. It wants to stay in its current state of rest. There is no net force on the book to move it, okay? Newton's first law. If I have a hockey puck on ice at constant velocity, what is the net force on the puck? Again, it's moving at constant velocity, which means its motion is not changing. What do you think?
Zero.
Has to be 0. In order for its motion to change in some way and have an acceleration, I have to have some force that's left over that's not being canceled out. And then for the question that people kind of don't like, I'll let you read it and think about it for a second. Really? No.
One.
Nah. You think it's 1?
Well, it can't. If no net force acted on it, by definition, it can't move.
Assuming that Newton's first law is working.
But
Which
law
works.
is working, I think.
It works in non-accelerating reference frames.
Isn't the bus moving? For it to stop, it would have to be moving.
The bus is moving and then slows down.
That's technically accelerating.
That is an accelerating reference frame, which means that things can move without a force. Newton's first law breaks if the reference frame is accelerating. This is the same as when you're on the plane, right? And the coffee ends up in your lap.
Ooh.
Nothing pushed on the coffee unless you have a really mean flight attendant who decides, or neighbor who's just like, haha, coffee in your lap. No, the plane accelerated. It's an accelerating reference frame. There was no net force, and yet it moved off the table. This is the exact same idea. You people are getting restless. Why so restless? Because you really want to leave. Okay, fine, go. I can't stop you. There's there's 3 minutes left, but I may just sit here and keep answering these questions because they're fun. Yeah.
On the homework, there's some problem about the circle speed in the 2 dimension. Is that going to be on?
That is on the exam, yeah. We covered the basics of circular motion in chapter 4, and you should have enough to answer those questions.
It talks about the radius, speed,
There should be enough there. Yeah. Bye.
What is the answer?
Have a good weekend. It's number 4. The stone ran out of steam.
I already left
No.
the answer.
In this particular case, we would say a net force acted on it all along to slow it down.
Why wouldn't it be 1?
That's talking about the initial kick, I guess. The force pushing the stone. There wasn't something pushing the stone the entire time that
What's
stopped.
the force that's acting on it all along? That
Friction.
friction.
And friction isn't the thing causing its motion. That's already over with. Friction is the thing stopping it. Yes. In the case of the truck, the thing in the truck, friction is making the object.
What was that?
Questions, things to say? Yes. What's up?
No, I was gonna be my so. Oh, good.
Yeah. How's that? Drum. Yeah. Okay. I'm gonna get mine. Right. If the drone is not being impacted by the elevator in any way, from your perspective on the elevator, it should go down. While from your perspective outside the building, it should stay.
What about or drive?
It may move it a little So if anything, it may not go down as fast, but it should still go down.
So you're trying to say that the force with the pencil, the amount of force that drove it on the ground. Or not the ground, what are the three principles for lift, drag, and
Gravity.
yeah.
So the drag is probably going to be, it's there, but probably not enough to worry about it. So essentially, if it's hovering, you've got lift that's being created by the rotors and the gravitational force, and that's all. And the acceleration is equal to zero, it's not moving up or down. So at that point, it's like if the elevator moves, the elevator is moving around it.
Exactly.
It should stay in essentially the same spot. But on the elevator, it's going to look like it's getting closer to 12.
Even in the vacuum,
Whether it's in a vacuum or in here,
that's the same.
it should be the same.
Okay.
If you have a drum, go play with it.
Wow, I don't wanna enjoy it, but it's something like that.
Probably a good call.
Yeah. Okay, thank you.
Yeah, cool.
Can you get up there? One time, see the sounds. It's 2 o'clock.
Yes.
You go ahead. You go ahead.
So I really the
Yes.
Well, I'm like,
Okay.
actually, can I ask a student after so the beginning of the as Tuesday?
Yeah. that's fine.
Oh yeah, I just studied the concept, but I just want like study problems.
Okay. If there's anything you want to ask over the weekend, you can email. Take a picture of what you're working on, and I can try to answer that.
Thank you so much.
You're welcome.
I
Pick
remember.
up.
I recently sent out an email. It's about the tutoring.
Yes.
Will they be able to help out if we get stuck on the phone?
That's what they found with me. Yeah.
If they said that they'll help out.
If they are worried about helping someone work, they can always contact me.
Well, I'll go there for sure. And anyway, the cheat sheet I remember you said it's like a full page front end.
Probably just front.
Just-
Probably.
Just front. Like I give you
Just a normal.
just front.
Mhm.
Alright.
Okay.
Yeah, I'll see you at 2.
I'll see you this afternoon.